Hi, I'm Pat Murray from Anritsu, and I'm working with Brian Shoemaker, and we're working on an application for making good measurements on unconnectorized differential lines for applications such as serial ATA, InfiniBand, PCI Express, and higher data rates. So earlier we did a video on how to extract the S4p files for the probes using an Anritsu VNA. So we're going to take use of those files and do the de-embedding for the probes to make this measurement. So today we're going to use the S4p files on a line that's a 2.5 gigahertz line, which is 25 gigabits per second differential line. So that's going to be our DUT. So it's a differential line with a PC board coaxial connectors on one end, and it's going to pads for the probes for the other end so we can touch down using those probes. So for the demo then, we're taking advantage of GigaProbes DVT40 probes and the Anritsu's VNA to make this measurement. So the measurement criteria then is basically having a VNA on the port 1 side of a differential measurement, and we're going to be calibrated at the end of our cables. We're going to go through a differential line to the pads where we're going to touch down the probes on the port 2 differential side of the VNA. So our calibration points are going to be at the end of the cables on the port 2 side, and we're going to de-embed the S4p files that we had captured in the last video, and de-embed those and show the effects of de-embedding versus non-de-embedding those probes. Okay, so for the demonstration that we're doing today, we have an Anritsu vector network analyzer connected to a GigaProbes board along with a GigaProbes probe, and we have a microscope that goes out to a PC so we can check connectivity. So, so that's the overall complete system. We'll take a look at the components inside the PC board. So so you can get a closer aspect of what the PC board looks like. So now this is where we did the calibration to the K connectors on the board. So we have coaxial connectors on one end. We have a differential line that runs through the board to some pads that touch down on the board where we can touch our probes and make the measurements. So we did a calibration up here at the connector types, and we're going to de-embed the file for the probe, so we have our calibration point is now going to be at the probe tips. We also have the microscope on here to make sure that we're making good contact on the probes. So it will look like the picture that we have over here on the side. We have the 2 ground pins and the 2 differential probe tips. So all of that now is we're moving that into the data inside the vector network analyzer and make measurements on this particular line and look at the effects of the probes that do not have a de-embedded file and the probes with a de-embedding file. Okay, so we've seen the measurement setup. Now we're going to take a look at the actual measurements. So we're going to sweep our Vectorstar from 70 kilohertz to 20 gigahertz because we're looking at a 12.5 gigahertz board. So, we've got 3 traces up. So trace 1 is the mixed mode trace for insertion loss, so that's D2, D1. We have trace 2 set up for mixed mode return loss, which is D2, D2, looking from the probe side coming back. And we have trace 3 set up for impedance measurement, so looking at D2, D2, again, looking at the impedance of the probes and the board itself. So those are the 3 traces that we're looking at. This is without the de-embedding applied, so we've calibrated to our coaxial connectors, and this is a response of the probe and the trace through the connectors. So now we're going to go take a look at the de-embedding portion of it. How do we extrapolate that S4p file that we built using network extraction before? So we're going to come into our de-embedding menu. So I'm going to select measurement, and I'm going to come into edit de-embedding and edit the network. And now I have a choice of selecting which ports I want to do my de-embed for. So since our probes are connected to the port 2 side, that's, in our case, that's going to be ports 2 and 4, and we're going to select ports 2 and 4. So I have those ports selected. I have de-embedding selected. I'm going to come down and pull an S4p file. So I'm going to go find that file that I did the network extraction on type G. So that's going to be D2 for port 2. And so I'm going to add him here. There's my file. I'm going to come over and I'm going to add him to my table. The reason I work from a table is because I can have multiple de-embeds. So I can come and start from my DUT and work my way down to my port connectors and do fixtures, attenuators, more lines, whatever I want to do. So now I'm going to apply that de-embedding file. I'm going to close this window and I'm going to turn my de-embedding on. And when I do, you'll see the differences between the measured data now and the extracted data file. So we're going to turn de-embedding on, and now you can see that we've de-embedded the probe. We have an improvement in the measurement from the through. We have an improvement in measurement on the return loss, and we, on the impedance graph, we've moved our probe from the point that it was out here over to the edge now of our connector for the very beginning of the sweep. So let's take a look at that, for example, since that's kind of one of the most interesting things of the measurement. So here we have the connectors on the board. This is actually the pads where the probes are touching down. Then we come through a line, a differential line, and it's approximately 100 ohms, as it should be. And then we kind of hit this anomaly right here. And then we come back up to about 100 ohms, and then we kind of hit an anomaly on the other side, and this is actually the end of the board because it shifted from out here to here because we de-embedded that section where the probe was at. So this is caused by a connector that is very, very close to this differential pair, and it's tightly coupled into our particular measurement, so that via actually shows up in our measurement, coupling across into our differential lines. So that via is here, and then we have the rest of our differential line. So it's very close to 100 ohms, so it's pretty decently matched line, and that's why the performance of that line works quite well up to 12.5 gigs. If we're actually look at the insertion loss at the 3 dB point, it actually works up to 13.1 gigs. So that's how you would de-embed the probe. I want to thank you for joining me today, and you have a wonderful day.